everyone! Welcome to another lesson in General Chemistry. Today's lesson is about concentration of solutions. Let's begin. First up is percent by mass. Percent by mass is computed by dividing the mass of the solute by the mass of the solution times 100%. Here's a sample problem. To maintain the same sodium chloride solution concentration as seawater, an aquarium should contain 3.5 grams of sodium chloride per 100 grams of water. What is the percent by mass of sodium chloride in the solution? The formula is mass of solute divided by the mass of solution, in which it is the sum of the mass of solute and solvent multiplied to 100%. For us to be able to compute this, we have to first identify which is the solute and which is the solvent in the problem. In here, the solvent is the 100 grams of water, while the solute is the 3.5 grams of sodium chloride. So to put this in an equation, 3.5 grams of sodium chloride divided by 3.5 grams of sodium chloride and 100 grams of water multiplied to 100%. 3.5 divided by 100, 3.5 times 100 will give you an answer of 3.4%. Therefore, this is the percent composition of sodium chloride in the solution. Aside from percent by mass, we also have percent by volume. Percent by volume is computed by dividing the volume of the solute by the volume of the solution. To compute, we have volume of solute divided by volume of solution multiplied to 100%. Here's a sample problem. What is the percent by volume of rubbing alcohol, an aqueous solution of liquid isopropyl alcohol, in a solution that contains 42 ml of isopropyl alcohol in 1.2 liters of water? So the formula is percent by volume equals volume of solute divided by volume of solution multiplied to 100%. Again, we have to identify which is the solute and which is the solvent in the problem. In this case, our solute is 4.2 ml of isopropyl alcohol, while our solvent is the 1.2 liters of water. In measuring the solution or solvent composition in a given problem, we use ml. Therefore, we have 42 ml of isopropyl alcohol over 42 ml plus 1200 ml times 100. To compute, the answer would be 3.38 ml of isopropyl alcohol. Next up, we have parts per million, parts per billion, and parts per trillion. If the solute is present in very low concentrations, then one of these units is used. 1 part per million means that 1.0 milligrams of solute is dissolved in 1 liter of water. At this concentration, the solution will have the same density as water, which is 1 gram per ml. Thus, we can write 1 milligram per ml as 0.001 grams of solute divided by 1,000 grams of solution. The same process can be done with 1 gram per liter to get 1 parts per billion and 1 nanogram or microgram per liter to get 1 part per trillion. Here's a practice problem to compute for parts per million. Find the concentration in parts per million of a solution in which 0.0059 grams of sodium chloride has been dissolved, making a solution with a volume of 750 ml. The formula is amount of solute divided by the amount of solution times 10 to the 6th power. In this, our solute is the 0.0059 grams of sodium chloride, and our solvent is the 750 ml of solution. Therefore, if we compute this, 0.0059 grams of sodium chloride divided by 750 ml solution times 10 to the 6th power will give us an answer of 7.9 ppm of sodium chloride. Now what about parts per billion? Here's a sample problem. Find the concentration in ppb of a solution in which 9.6 times 10 raised to negative 6 grams of sodium chloride has been dissolved, making a solution with a volume of 2 liters. The formula would be amount of solute divided by the amount of solution times 10 raised to the 9th power. In here, our solute is the 9.6 times 10 raised to negative 6 grams of sodium chloride. And our solution is 2 liters or 2000 ml. To compute, we have 9.6 times 10 raised to negative 6 grams of sodium chloride divided by 2000 ml of solution multiplied to 10 to the 9th power, giving us an answer of 4.8 parts per billion of sodium chloride. How about parts per trillion? Now here's a practice problem. An Olympic-sized pool is 50 meters or 164 feet long, 25 meters or 82 feet wide, and 2 meters or 6.6 feet minimum deep. It holds 660,000 US gallons or 2.5 million liters of water. It has 8 racing lanes that are 2.5 meters wide with an empty lane of 2.5 meters in width along each side. While there are 10 lanes, only the middle 8 are used for racing. If 1 gram of sodium chloride is dissolved in the water of a pool of this size, what is the concentration of the dissolved salt in parts per trillion? Now the formula for getting parts per trillion is dividing the amount of solute and the amount of solution multiplied to 10 raised to the 12th power. We have to identify first which is the solute in the solution. So the solute is the 1 gram of sodium chloride, while our solvent or the solution is composed of 2.5 million liters of water. Since we are using ml, we have to convert 2,500,000 liters of water into ml by multiplying it to 1,000. So the final equation would be 1 gram of sodium chloride multiplied to 2.5 billion ml solution times 10 raised to the 12th power, giving us an answer of 400 parts per trillion of sodium chloride. The next one is molarity. The most common and one of the most used units of concentration is molarity. It is defined as the number of moles of solute in 1 liter of solution. Molarity is denoted as capitalized letter M and has a unit of mole per liter and is read as molar. So the formula in getting molarity is by dividing moles of solute over the liters of solution. Here's a practice problem. What is the molarity of a bleach solution containing 12.5 grams of NaOCl per liter of bleach? So first, we have to get the molecular mass of NaOCl. Sodium has 22.99 grams per mole. Oxygen has 16 grams per mole and chlorine has 35.45 grams per mole. Adding this up, we'll get an answer of 74.44 grams per mole. Then, we have to get the number of moles of NaOCl, in which, since in the given we have a sample of 12.5 grams, this will be multiplied to 1 mole divided by 74.44 grams. So 12.5 grams times 1 mole divided by 74.44 grams will give us an answer of 0.168 moles. Now that we already know how many moles is NaOCl, we now compute them. Again, molarity is computed by dividing the moles of solute and the liter of solution. So we have 0.168 moles divided by 1 liter. And the answer is 0.168 mole per liter. Now let's move on with molality. Molality is another unit of concentration. It is similar to molarity except that the number of moles of solute is divided by 1 kilogram of solvent rather than 1 liter of solution. Using molality instead of molarity is advised if calculations are performed over different temperatures since volume is dependent on temperature. The unit for molality is small letter m, which is read as molal. Again, the formula in getting molality is moles of solute divided by the kilogram of solvent. 1 liter is equivalent to 1 kilogram. Now here's a practice problem. 3 moles of sodium chloride dissolved in 2,000 grams of water has a concentration of 1.5 meters of sodium chloride water solution. The computation is given below. Since we already know the number of moles of sodium chloride, we just write it. Then, the kilogram of the solvent. Since on the given, we have 2,000 grams, we have to convert it into kilograms by dividing it into 1,000, getting us an answer of 2 kilograms of water. So 3 divided by 2 will give us an answer of 1.5 moles per kilogram. Now the last one for the concentrations of solution or expressing concentrations of solution is mole fraction. Some properties such as vapor pressure need the solution concentration to be expressed in terms of mole. Mole fraction is defined as the amount of the component of the solution expressed in moles per mole of solution. Mathematically, mole fraction is equal to the moles of the component divided by the total moles of all the components in solution. X represents the mole fraction and I denotes the solution component in question. More specifically, the mole fraction of the solute can be written as X sub A, while the mole fraction of the solvent can be written as X sub B. Thus, the expression for X sub A and X sub B are as follows. X sub A is equal to N sub A over N sub A plus N sub B. Then for X sub B, we have N sub B divided by N sub A plus N sub B, where N sub A is the number of moles of solute and N sub B is the number of moles of the solvent. Now, how do we compute for mole fraction? Here's a sample problem. What is the mole fraction of hydrogen chloride in an aqueous solution that contains 44.2 grams of hydrogen chloride and 88.6 grams of water? Again, the first thing that we need to do is to identify which is the solute and which is the solvent in the problem. In this case, our solute is the 44.2 grams of hydrogen chloride, and our solvent is 88.6 grams of water. Since mole fraction is expressed by mole, we have to get how many moles does this grams have. The first thing is to get the molecular mass of hydrogen chloride. So hydrogen has a mass of 1.01 gram per mole, and chlorine has 35.45 gram per mole. Adding this up, we'll get an answer of 36.46 grams per mole. Next, we have to get the number of moles of hydrogen chloride. Since on the given, we have 44.2 grams of hydrogen chloride, we have to multiply it. To every 1 mole, we have 36.46 grams. So 44.2 grams times 1 divided by 36.46 gram will give us an answer of 1.21 moles. Therefore, this is the number of moles of hydrogen chloride in the sample. Next, we have to get the number of moles of water. So first, we have to get the molecular mass of H2O. Hydrogen has a mass of 1.01 gram per mole, multiplied to 2 because it has 2 atoms. And oxygen, which has 16.0 gram per mole. Summing this up, we have 18.02 gram per mole. Then, we get the number of moles of water. Since on the sample, we have 88.6 gram, we have to multiply it by, in every 1 mole, we have 18.02 grams. So the final computation would be 88.6 gram times 1 divided by 18.02 grams. We'll get an answer of 4.92 moles. Therefore, on the sample given, we have 4.92 moles of water. Next, since we already computed for the number of moles of our hydrogen chloride and water, let's proceed with the computation of the mole fraction. On the problem, we have to get the mole fraction of HCl. And since HCl is our solute, the formula to be used is X sub A is equal to N sub A divided by N sub A plus N sub B. So the mole fraction of the aqueous solution is 1.21 moles divided by 1.21 moles plus 4.92 moles. 1.21 mole come from the number of moles of our solute, which is the hydrogen chloride. And the 4.92 is the number of moles of our water. So 1.21 mole divided by 6.13 mole will give us an answer of 0.197 moles. So this is the mole fraction of hydrogen chloride in the aqueous solution. Here's another sample problem. What is the mole fraction of ethanol in a solution prepared by dissolving 150.0 grams of ethanol in 100 grams of water? Again, in order for us to solve for the mole fraction, we have to get the number of moles of both ethanol and water. Let's start off with water. So get the molecular mass of H2O. Hydrogen has 1.01 gram per mole. Since we have H2, we multiply it by 2. Then oxygen has 16.0 gram per mole. Summing this up, we'll get an answer of 18.02 gram per mole. We already get the molecular mass. Now let's get the number of moles. On the problem, we have 100 grams of water. So this is our sample. Multiplied to, in every 1 mole, we have 18.02 grams. So 100 divided by 18.02, we'll get an answer of 5.55 moles of water. Next, let's get the number of moles of ethanol. Starting off with getting the molecular mass of C2H5OH or ethanol. We have two atoms of carbon, so 2 times the molecular mass, which is 12.01 or 24.02 grams per mole. Hydrogen has 6 atoms, so 6 times 1.01 is equal to 6.12 grams per mole. Oxygen has only 1 atom, so 1 times 16 is equal to 16.0 gram per mole. Adding 24.02, 6.12, and 16, we'll get an answer of 46.14 grams per mole. Now that we already get the molecular mass of ethanol, let's solve in getting the number of moles. So to get the number of moles of ethanol, we have to multiply our molecular mass with the given grams of the sample. So 150 grams of ethanol multiplied 2. In every 1 mole of ethanol, we have 46.14 grams. Therefore, the computation would be 150 grams times 1 divided by 46.14. We'll get an answer of 3.35 moles. Okay. Now that we already get the number of moles of both ethanol and water, let's solve for the mole fraction. Now that we already know the moles of ethanol and water, let's solve for the mole fraction of ethanol in the solution. So the formula would be X sub A is equal to N sub A divided by N sub A plus N sub B. So since we're getting the mole fraction of ethanol, so we have 3.35 moles of ethanol divided by 3.35 moles plus 5.55 moles. 5.55 is the number of moles of water. So 3.35 moles divided by 8.85 moles will give us an answer of 0.3785 moles. Therefore, this is the mole fraction of ethanol in the solution. Thank you for watching, and remember, think like a proton, always positive.